seems to be causing the most difficulty is number 9. So we've got a surface here, which is a hole. It's the surface of a tetrahedron. So that's a multi-sided surface. And it's created by the coordinate planes and this plane. Right here, right? It's a plane. Okay, so this plane, when y and z are 0, it goes through x equals 4. When x and z are 0, it goes through y equals 5. And when x and y are 0, z is 4. So that's a quick way to sketch this plane. It's going to go through 4, 0, 0, 0, 5, 0, 0, 0, 4. So then when you get just the part of that in the first octant, there's our tetrahedron. It's a 4-sided figure. Do you see that? It has this triangular slanted top and then 3 other triangular sides, which are in the coordinate planes. And so we got this vector field here that this thing lives in, and we want to find the surface integral of that closed surface, right? So the surface is actually made up of so that surface integral will be the sum of what? 4 surface integrals. And so you have to parameterize each of those first surfaces, and then find the cross product, and then add up these 4 surface integrals. Is that right? Okay. Doing that, would that be using the divergence theorem to calculate the flux across that closed surface? No, it would not, because the divergence theorem says that this equals what? Triple integral of over the solid of the divergence of f dv. So using the divergence theorem to find this, using the divergence theorem means doing what? Calculating that. This is a theme on the final. And if you don't get this theme, you will do very poorly on the final. The idea of using a theorem to calculate something means you don't calculate that something. The theorem says it equals something else, and you calculate that. Because this is a very important point on the final exam. Okay? Because we're going to have, in the end, we're going to have 4 fundamental theorems, right? We're going to have 4 fundamental theorems in vector calculus. And I'm going to be asking you to use those theorems, okay? So in this case, so instead of doing this, we don't do this. We could, and we've done examples like that. But now instead, we're going to look at this solid E and do that divergence, or find the divergence of f, and then calculate the triple integral. So my guess is maybe if you were doing, so you probably had difficulty if you just tried to do the straightforward flux integral, then you could run into problems there. But if you did pick up on the theme of the problem, which was to actually do a triple integral of the divergence, then the difficulty is that a triple integral of a tetrahedron is algebraically not smooth sailing. Okay, there's lots. You have to make sure you have everything. To be very careful, right? So you're going to solve this for z. So if you want to do the divergence of f is really easy. But then say if you want to do type A1, dz, dy, dx, then you have to solve this. You're going to go what? Bottom to top. So 0 to z equals. Solve this for the plane. And then what do we do? What's then from there? What do we do? Right. Project the surface into the xy plane and do a double integral over this triangle. So you're going to have to write the equation of this line. 5 minus 5/4 x or something like that. Anyway, so so this is then you're going to be your double integral projected for the region projected into the xy plane. So the algebra may get kind of long and tedious, even in but it's probably still easier than doing these 4 surface integrals separately and adding them together. Okay, so how many? You get 7 attempts. So those 7 attempts are for, all the natural pitfalls you could find in the algebra. Okay. So just work the algebra very carefully. Questions on this problem? Okay, so you got until midnight tonight. The rest of it looks like we're having some success at, so we're just going to move on to the new stuff. So one thing I should mention is that since the last exam, we've had a lot of theory in class, a lot of important theory, important ideas and concepts. The web work has focused more on solving the problems. Okay, both are important for the final. So I strongly suggest, and I'm going to post study resources by tonight. So if I can't get that this afternoon, I'll do it tonight. Get your study resources up for the final, which is a week from tomorrow night. But you're going to have to go back and watch those videos and take new notes, review your notes, but watch those videos and make sure you're getting the ideas and concepts, because there wasn't a lot of practice in that aspect of it. Most of the practice you got in the web work was just solving the problems. And as you know, I'm very interested in seeing if you understand things, not just can you regurgitate these problems, okay? So make sure you go back and watch videos and review your notes for all this stuff that we've done since the 3rd exam, because that is important. Okay. Any questions about things? Yes, sir?
How big is the final?
What's that?
How big is the final?
How big? Really big. Huge.
What's the layout of the final one?
What's that?
Do you know what the layout of the final is going to be like?
So it's both multiple choice and free response, and it's, I don't know what I said, 30% of your grade? 20 to 25? Yeah, it's somewhere from 20 to 30. I'm guessing 25. But here's the deal with this. If you do better on the final exam than you do overall in the course, then I'll weight the final more for you. Does that make sense? Because it's a cumulative final. So for instance, if you get, let's talk about this quickly. If you take the final exam and I calculate your grade in the course as I promised on the syllabus, and you have a 77 in the course, okay? After just exactly the way I promised on the syllabus. But to get that 77, you had a 83 on the final. That was with an 83 on the final. Then I'll give you an 80 in the course. I'll average those again, and I'll give you 80% in the course. So that's making the final exam worth like more than half of your grade when I do that. Okay? But if you got a 77 in the course and that was because you got a 72 on the final, then you'll just take the 77. So it's only for those people that do better. So I will give you what I promised you on the syllabus. But if you do better on the final than your overall in the course, I'll make the final worth more. And so that's the kind of thing that will happen. Okay, so there's more hope than you thought, maybe, okay? But that means you have to study on the final. That means you have to do well on the final, like better than you did on the hour exams. So start studying soon. Don't start studying on Saturday, okay? Especially not, when is it, Tuesday night? Yeah, I would suggest, see if you can start carving out some time in the end of this week, and so you can really hit it hard this weekend and then get your questions answered Monday and Tuesday. You're going to learn the most when you have conversations with each other and with me. So we'll have some study session or something on Monday or Tuesday, and then get with me, and the conversations that we have about the work that you've done is going to be where your understanding can increase the most. Okay? So find me, ask me questions, get your questions answered. And then have study groups too. Study in groups and talk. The more you talk, that's the stuff you remember when you talk. Sarah?
So for next week, are you going to hold office hours or is it just
Yeah, we'll have like a study session. with me there, and Key hopefully can come too. So yeah, and I'll post that, but it won't be like after this Friday. So the last normal office hours are today and tomorrow, and then I'll post special hours next Monday and or Tuesday. Okay? All right. So one last topic. So we talked about last week. We talked about flux density, right? Flux density was like how much flux per volume. So now I'm going to talk about circulation density. Circulation density is so circulation density is a similar parallel topic to flux density. So before we talk about that, we got to talk about orienting a boundary of an open surface. So we talked about orienting a closed surface. Yeah.
Did you start the recording video?
I don't think I did. Yes, I did. Thank you. No, thank you for asking. Yeah, thanks for asking. All right, so what do we say? So you said flux density was like how much flux per volume. So we'll talk about circulation density as kind of a parallel idea to that. But before we talk about that, orienting a boundary to a surface. So we talked about orienting a closed surface, right? And so what were the possible orientations of a closed surface? What could you do for a closed surface? Yeah. So yeah, either in or out, right? So that's what we said, either in or out. So so suppose we have an open surface. Now we're talking about open surface, right? So that was a closed surface. An open surface S with a boundary C. So we know that we can orient that like the way it's shown here. This one would be like either up or down, right? It's either up or down. So what about orienting the boundary of that surface, right? So what about orienting the boundary of that surface? So what you can do is you can look at a little a vector n close to the boundary, and by the right-hand rule, that can help you determine what the orientation of the boundary is. So like here, so if we're orienting upward, so I'm showing that we're orienting S upward. So if you take a little n then close to C, and by the right-hand rule, that will be what, clockwise or counterclockwise? Counterclockwise, right? So if your thumb points up and your right hand, it'll be this way. So that means like this, right? So then if you look at where that little circulation path gets close to C, that shows you that you're gonna orient C that way. See that? So as it comes and gets close to C, we're gonna orient C the same way as that little loop according to the right-hand rule for n. So that's why it goes this way. Does that make sense? So let's just see if that is consistent with this. So I chose another n here back by the back edge, right? So right-hand rule means what? Counterclockwise. Again, like this. So then when it gets close to the surface, close to the boundary C, so back there in the back, is C going to be oriented from left to right or from right to left? Right to left. So you see, as it's curling it back around this way, it's going to be consistent with C going this way. And then is that consistent with what we had over here? Yeah. Right? So it ends up in this example that it's going to be counterclockwise, right? Counterclockwise. All right, so here's another open surface that actually is like the sleeve of a circular cylinder. So it's open in the top and the bottom. So like water would just run right through this. So if we look down, so there's actually two parts to C, right? C has this part and this part. So right-hand rule means counterclockwise. So we're going around this way for outward orientation of S. We're going to go around this way. So then we'll see that this top part of C in the front here, is it left to right or right to left? Left to right or right to left? Right to left. So it's going to go the same direction along here as this going along here when it gets close. Okay, and then down here. So again, counterclockwise for the outward orientation of N. So as we get close to C down here, this is going to determine the direction of C going this way. So left to right or right to left? This time it's this way, right? And then back around like that. So notice that they're opposite, right? So this is going around this way. This is going this way, right? The top part of C is like that. Bottom part of C goes around like that. But they both still follow this idea that if you're walking on C, the surface is to your left, right? So if you're walking on C here, you got to think about walking kind of like the man is kind of like pointing out at you guys. Sorry, maybe it's a woman. Okay, so walking around this way, and so then, do you see that walking around this way, the surface is on the left? Do you see that? And then same thing here. Again, walking around. If they walk around this way, surface is on the left. So it's still consistent with that. The orientation is walking around so that the surface is on the left side. Okay, did you follow that? Does that make sense? Any questions on that? Okay, so recall that our circulation around C, that's just our line integral, right? So it's given by the line integral. We could even make it one of these, right? So circulation integral has a little circle on there. So it's a line integral, f dot dr. So we did line integrals a couple weeks ago, and it's my experience in the course that we do all these surface and triple integrals, and for some reason line integrals just kind of like fall out of all of our brains. Make sure you know line integrals. Line integrals are super important, okay? So if you've forgotten, you got to review that. All right, so what's circulation density? So circulation density is the strength of circulation, and it's like looking at the line integral per the area inside. Just like the flux density was the surface integral per volume inside, this is going to be the line integral per area inside. Okay, and you can choose any direction V for circulation density. Choose any direction V, and you're asking about what? The circulation in the plane orthogonal to V, right? Because circulation is the direction of circulation is always orthogonal to the kind of the circle of rotation. So when you choose a direction V, you're saying how much strength of circulation is this way. See that? And if I choose V to be like this, I'm saying how much circulation is there this way in the plane orthogonal to V. Okay, so here's the notation for that. Circulation, so sub V, meaning here's the direction of the orthogonal to the plane of the vector field. So that's the notation we use for circulation density of the vector field F in the direction of V, which again means rotation in a plane orthogonal to V. Okay, so like the flux density, it's going to be this limit. It's the limit as the area inside your circulation path goes to 0 of the circulation divided by the area. So this is totally parallel with the idea of flux density. So it's kind of like, how much, remember one way we thought about this was like accumulated work in a force field. So like, how much work do you accumulate going around? How much work is done going around per how much area is inside? So if you do a lot of work for a really small area, it's a really strong rotation, right? Really strong rotation. And if you do just a little bit of work for a really big area, that's not very much strength of rotation, right? Okay, so then we can choose, what we want to do then is if we have a surface, we want to choose V to be the direction of n, right? We want to choose V to be the direction of n, and so then we're looking at the strength of circulation kind of within, parallel to the surface, right? In that plane parallel to the surface. So if n is orthogonal to the surface, it's kind of like we're looking at, if we choose V to be here, then we're looking at the circulation density for that kind of rotation. So what is circulation density? Does it feel like anything we've seen before?
Curl.
Right, so we said curl was, that's exactly what we said curl was, right? The strength of rotation. So if we choose V to be in direction of n, then the circulation density in the direction of n for some surface is the curl. But it's what? Only as much of the curl as is in the direction of n. So that's why it's the dot product with n, right? So it's curl dot n. So it's like we're taking the component of the curl that's in the direction of n. That's why it's dot product. And so then we get this like strength of rotation in a plane parallel to the surface. Okay, so the circulation density in the direction of n is the magnitude of the curl of F and as much as it is in the direction of n. So that summarizes what I just said. Okay, anybody have a question? Yeah?
For the last part of the equation in the middle, is that a circulation integral, not just a regular line integral? Would it be a circulation integral?
You mean a little circle here? Yes.
Alright.
So it is. Yes, sir.
Are you always to calculate this with the limit way or with the cheat way when we want to curl?
Yeah, no, so this is just, there might be something where you have to use this, so just make sure you know that that's what that is, but we're kind of going somewhere with this. Yeah, so it's possible that there would be a problem where it would be specified this way. Other questions? Okay, so picking off where we left off there. So this is exactly what I had at the bottom of the last screen. So here's our surface, and so I'm showing the n vectors in red, and then I'm showing the curl of F. And so when we do curl of F dot n, then we're going to take only as much of those blue vectors, the component of those blue vectors in the direction of the red vectors. Okay, so we're seeing that the curl of F is going to give another way of calculating the circulation, because the circulation integral, we know, is related to the circulation density, right? So this circulation density has everything to do with the value of this integral. So we're going to see that the curl of F gives another way of calculating C. So, and by C here I mean, right, C is the boundary of S. So far all we know is that we'd have to just parameterize this path and add up the 4 line integrals to get that circulation integral. But what we're seeing then is that the curl of f is going to give us another way to calculate that same value. So we're going to look at, so we're going to break this surface up into elements like we've done before. So if I broke this surface up into elements, and so let's look at this element right here. And for this element right here, we have this is the curl vector, the blue one, and then the red one's the n vector for the surface. So focusing on that right there. So this little path here is like a delta C, and then the area inside is delta S. Okay, so we're just going to focus on one little element. Again, around there is delta C, and then inside is delta S. So what is the circulation? The circulation is, we saw this on the previous screen, it's the limit as our, so now we're just looking at the circulation for that one little element, and so it's going to be the line integral around delta C divided by the area delta S. Delta S. So then when things get small, so then we're going to imagine that as things get small, then just imagine this is a really small element around there, and so then it's going to be the little line integral around a really teeny element over a little small area, ds. So then what does that mean that this equals? So then therefore this integral, this little circulation integral around a little teeny element is going to be, so I'm just multiplying both sides by ds. You see that? It's going to be the circulation times ds. So I just basically solved for this right here. This equals this times this. Okay, but we said that the circulation is the same as the curl of f dot n. Right, so that's the same as that. So our little circulation integral around an element is equal to the curl of f dot n, or the strength of rotation, times the area of that little element. And then what we're going to do is we're going to add them all up, okay? So we're going to add up all the circulation, the little teeny circulation integrals for all the elements on the surface. Add them all up. And then there's two ways we can go with that. And the first way is we're just going to add up a bunch of these. Right? So for each little element, we're going to be adding up the curl of f dot n, which is the part of the blue vector that's in the direction of the red, times ds. Okay, so and what is this? What is this principle here? That we're going to add up all these little perpendicular vectors to the surface, or kind of accumulate all these perpendicular parts of the curl that's perpendicular to the surface. What is that? It's an integral, right? But what kind of integral? What's the key word here? If we're looking at so we've got all these blue vectors. We're going to take the part of the blue vector in the direction of the red, and we're going to accumulate all those for the whole surface. It's kind of like what? It's kind of like the amount of flow through. Flux, right? So this is the flux of the curl. So it's not the flux of F, it's the flux of the curl, right? So it's how much flow of rotation, right? So it's how much flow of rotation, and that rotation is actually what? The rotation itself is actually parallel to S. So then it's the flux of that through the surface, right? Because for vectors perpendicular to the surface, we're talking about rotation parallel to the surface, right? So it's kind of like summing up all the rotation parallel to the surface, and then that's like the flux of the curl through the surface. Okay, the other way we can go with this is we can do what we've done before. We can say, when we do these little circulation integrals around every element, what happens? All the shared sides cancel, right? All the shared sides cancel, leaving just the circulation integral around the boundary of C. Okay, so that's the other way that this calculating all these little circulation integrals for all the elements with all the cancellations on the inside leaves us with just the line integral around the boundary. So summing up all the little flux of the curl for all the little elements, so that's, we know the flux is our surface integral, right? But now it's the surface integral of the curl of f, not the surface integral. All the surface integrals we did were just given an f, find the surface integral, right? The flux through it. But now the curl is a new vector field, and we want the flux of that because we're actually talking about the flux of kind of rotation in every element, right? So these both give us the total sum circulation for around every element C, they're equal to each other. And so this is what Stokes' theorem is. So given an orientable open surface S with a boundary C whose orientation is determined by n, then the line integral around the boundary of that open surface is equal to what? The flux of the curl of F through that surface. And what kind of thing did we say the curl of F was relative to F? What we said the curl was? Rate of change, right? Vector fields have two rates of change, right? Curl, rotational rate of change, and what the other one was? Divergence, expansion rate of change, right? So, look, this is a rate of change of F. And we're going to use that rate of change to get little amounts of flux, right? Little amounts of flux. And then we're going to sum up all the flux by adding all that up. And that's going to equal what? Kind of like a total change around the boundary, right? Total change around the boundary. And so what's that about? Sort of like total net change. This is a theme we've mentioned before. What's the theme here? Yeah.
It's an accumulation of a bunch of low rates of change to total.
We're not accumulating rates. Be careful. So what are we accumulating?
You're accumulating little vectors.
Amounts of flux, right? So, yeah, we're accumulating little amounts of change using the rate of change. We're not accumulating the rate. So we're accumulating little amounts of change using the rate, and that equals the total net change around the boundary. Have we talked about that before?
Yes.
And what is this? This is the fourth time we've seen it, I think.
It's like all the theorems are doing, just this is
Right, what is it? What all? Fundamental theorem, right? Fundamental theorem of calculus, right? Fundamental, right backwards. So we're seeing it again. This is the theme. We saw it with Green's theorem. We saw it with the fundamental theorem of line integrals. We saw it with the divergence theorem. They're all fundamental theorems of calculus, so they all have these qualities that you use rate of change, what, to calculate a bit of change. In this case, a little bit of flux for a little area element. And when you sum up all that flux over the whole surface, it's the same as the total net change you'd get around the boundary. Right? The total net change of the original vector field around the boundary. So this is our final fundamental theorem. So we've got fundamental theorem of line integrals, Green's theorem, divergence theorem, and Stokes theorem. Okay, so let's look at an example here. And this example is like simple and really helps drive home what's going on here. Any questions so far on this? Okay, so I've got a it's too small. I got this vector field here, and it's negative 2x, negative 2y, 2x, 0. So let's write that down. And I've got this path C here. It's a circle. It's a circle in the plane x equals 1. Circle, radius A. In the plane x equals 1. Okay, and we want to examine Stokes' theorem for this, right? So we're going to examine Stokes' theorem for this circular path in the plane x equals 1, and the circle has radius A. Okay, so the first thing we want to do is really what do we care about? Do we care about all these vectors in the vector field? What vectors do we care about in this vector field? Just the ones in the plane x equals 1, right? That's all we really care about. So let's look at that. So here's just kind of just the vectors in the plane x equals 1 of that vector field, negative 2y, 2x, 0. So the first thing we look at is, in Stokes' theorem, is let's look at the line integral. Okay, so we should be able to do that. What would doing that line integral entail? What would we need to do that, just as a review? Parameterize the curve, good. We're going to parameterize the curve. And then f in terms of how we parameterize the curve. Let's just do it. It's not hard. So r is going to be t, sorry. So remember with curves, you get one variable, one parameter to write either both components or all three. Here it's going to be 3, right? We have an x, a y, and z component. But we only get one variable to write all 3 components because it's a curve. So what's x going to be? 1. It lives in the plane x equals 1. What's y going to be? So y a cosine t. And then z will be a sine t. And then we'll rewrite f, so we'll just set it up, we won't solve it though. So we're going to go, t is going to go from what to what? 0 to 2 pi of f is negative 2y, which is Negative 2a cosine t. And then 2x, or sorry, yeah, 2x is going to be 2 and 0 dot dr, right? So what's dr? 0, negative a sine t. So instead of solving that, we could solve that out. We're going to just predict it. We're going to look at it. So let's look at this. So here's the part of f that matters, and we're going to do a line integral around that. Negative, 0, or positive? What do you predict? I have a vote for negative. I have some votes for 0. You change your mind?
Yeah.
0, right? See, by the symmetry of this, we're going to have what? Some negative, as we're going, we're going to have some negative contribution here. It looks like the exact same positive contribution in the second half, right? Cancel out. So we think that's going to be 0. So now what does Stokes' theorem says that that's equal to what? The flux of the curl. So let's find the curl. The curl of negative 2y 2x 0. We're going to find the curl. Curl is, this is where we do the operators, right? We do the gradient operator as a cross product. Those are not 2's, those are deltas. These are 2's. So what's the curl going to be? Looks like the partial of 0 with respect to y, and the partial of 2x with respect to z, 0. Partial of negative 2y with respect to z, partial of 0 with respect to x is also 0. And then k. Partial of 2x with respect to x, 2, minus the partial of negative 2y with respect to y, 4. So what does the curl vector field look like? What does the curl vector field look like? Just all vectors pointing up at 4. So let's show that. There's the curl in the plane that we want. There's the curl in the plane that we want. And so what does Stokes' theorem says? Stokes' theorem says that that circulation integral that we calculated is the same as the flux of the curl, right? The line integral of the curl. What is S here? What is the surface S?
Just the after.
No, it's the surface, right? So C is this. So what is C the boundary of? This disk, right? So it's just like this filled in, the filled in hole, or the disk. This is what the S would be. Okay, so we do the flux of the curl, or the flux of this blue vector field, accumulation of that through this disk. What is it? What are all those vectors? So it's like how much of this blue vector field do we get flowing through? 0, right? Because it's all the flow is parallel to the surface. See that? All the flow is parallel to the surface, so the flux of the curl is 0. And we could do the math. This is a case where we could use the dot n, right? Dot n ds. So the curl is 0, 0, 4. And what is n? For that disk in the plane x equals 1. 1, 0, 0. So we see that it is 0. So you see what happened? So the line integral around the boundary of the original vector field F is 0, and the flux and the curl is parallel to that plane. All the curl is in the positive z direction, so there's no flow through that surface S, and so we get 0. So it's like we verified that it's 0 for both. Good so far? All right, so let's look at a different circle. Can I erase what's up there? Let's go back to this. We'll go back to the original. Let's look at this circle. So here's our vector field. Same one, minus 2y, 2x, 0. Or sorry, is it minus 2y, minus positive 2x, 0. Okay? And so this is in the plane z equals 1. So now we have the circle, radius a, in the plane z equals 1. Radius a, not 1. Okay? And so we want to, so what, again, in terms of doing that line integral around that path, what part of this vector field do we care about? See if this works. Good enough. So we really just care about the kind of the vectors in that plane of that circle, that part of the field. So prediction for the circulation integral, negative, 0, or positive? It's going around the whole way, right? Positive contribution the whole way around this thing. So we would expect that. Just by looking at this, we would definitely expect that circulation integral to be positive. And we could do it. We could parameterize this new circle, and we could calculate it. We got the vector field, we got the parameterization of the circle, and we'd be good. Yeah?
So we just assume that the circle's going counterclockwise?
That's positive orientation, right? So we have to be consistent with if we call the, so yeah, we oriented ourselves, right? But now when we look at the surface, we have to make sure they're consistent. Yeah, so we decide which way it goes, and so for clockwise orientation, we'll get a positive integral. Yeah, so we choose, okay? So we just now have to be consistent now when we look at the double integral. So when we look at the double integral, we're going to look at the flux of what? Again, the curl, right? So the curl was 004. And we want just the part of the flux in that plane. So here's the curl. And since we chose positive orientation to be counterclockwise, then our positive orientation of the surface will be upward. And so what do we expect for the flux? Positive. Let's do it. Ready? So we're going to we're going to figure out what that line integral was that we expect to be 0. So the curl is still 004, right? Zero, 1. Okay, and then we need ds. And so again, we're going to do, our surface is going to be the disk inside there. So what's the best way to do that double integral? We're going to use polar, right? We're going to use polar. And so if we do polar, so we're going to, this dot product is 4. But the ds now, the ds is going to be our dr d theta. And then r is going to go from 0 to a, theta, 0 to 2 pi. So if we factor this 4 out, we're really going to get what? 4 times, what does this integral calculate now? 0 to 2 pi, 0 to a, r d theta. The double integral calculates area of the disk, right? Because it's 1 dA, right? So it's going to be 4 times pi a squared. So the flux of the curl, 4 pi a squared. The line integral, the circulation around the boundary, also 4 pi a squared by Stokes' theorem, which is greater than 0, which we predicted. So yeah, so when you have a positive curl, positive circulation around the boundary, that means that the net sum of all the curl in the inside has got to give you positive flux through the surface. That's what we're saying. See that? Okay. Hit the books.